in more than 30 years of experience, or combined close to 100 years of experience in both aquatic sciences, in stormwater monitoring and modeling. Bill Taylor has over 35 years of experience and has worked really extensively in assessing streams, lakes, and coastal ecosystems. Dodd brings over 40 years of experience and was one of the co-founders of Clear Creek Solutions. He has a really strong experience in modeling, especially with WWHM and HSPF, and we're really excited to have them both today present about their recent projects. So with that, I'll pass it to you, Bell and Dodd, and you take it away.
Very good. Thank you, Eamon and Michelle. And really glad to have this group of mostly engineers. We're interested to hear from the engineering community. We have been presenting to stormwater managers and other permittee representatives, but this one will be a little bit special with the engineering community. I'm going to share my screen here. And Eamon and Michelle, are you able to see the presentation?
Yes, we.
Okay, very good. This is the Bioretention Hydrologic Performance Study, Phase 2. Our team is with us also, so we have myself, Doug Beyerlein, and also Jenny Saltonstall, and I believe Brian Verkompis that did the hydrologic monitoring, and Ann Klein, our professional landscape architect, on for those questions. This is an NPDES permit-funded project, and City of Olympia gratefully is our sponsor, and the ecology staff helping us. I'm going to go fairly quickly so we can get to Doug's portion. But the purpose of Phase 2 was to assess bioretention facilities designed with WWH with the bioretention module. And if everybody could mute, please, I can hear a microphone going. And the idea was to evaluate the hydrology of 10 built facilities. In other words, how well do constructed bioretention facilities perform compared to their design models? Many of you, I'm sure, are intimately involved in designing and modeling these facilities. And what conditions may be causing differences between the actual performance and model performance? We actually model hydrology in the field, starting with rainfall and inflow through a compound weir like you see here. So we're getting on the ground measurements. As Phase 2 might suggest, there was a Phase 1. The first 10 in Phase 1 were not designed with WWHM2012, so they didn't use the bioretention module, and they were generally older. The second 10 were in fact designed with 2012, and of course were only recently built. Here's the distribution of the sites, 10 sites, all the way from Bellingham in the north to county in the south, with an river in between. I'm going to go through some photographs of the facilities so you get an image of what they look like on the ground. These were some facilities in the first 10, and that is Ann Klein, our professional landscape architect. Here's one from the current set of facilities, and this is a retrofit, which was one of the main differences in the selected sites in this set of 10 compared to the previous set. And the retrofit is, of course, kind of fit in or constructed into existing infrastructure. And the main difference is under the stormwater manual, there are not design criteria required for those retrofits. And there's a lot of latitude given to the engineer to design it as with best professional judgment to make an improvement in hydrology and water quality. Here are some other facilities that are part of the current study. You can see they were all very recently planted. Most cases, we monitored in the first year of their performance. Here's one that was not selected, but it was part of a site that was still under construction, and you can see what that construction looks like. There's one in Marysville that was unique in that behind it, adjacent to it, was tidal channels beyond the cyclone fencing there, and the groundwater monitoring saw some fluctuation as a result of that tidal influence, but it did not affect the infiltration performance. We assessed the various parts of the system, facility dimensions, bioretention soil and subsurface composition, did infiltration tests, measured the hydrology, and categorized the vegetation between herbaceous and shrub composition. These are all the parts that come together to affect the performance. And our findings with the dimensions were that 3 facilities had smaller bioretention areas than reported, and 6 of the facilities had very small ratio of bioretention area to drainage area. I'll go through this table for a moment. Here's the list of the sites with their acronyms. The R and U just indicates that they are a retrofit and or underdrained. And the red figures show the facilities that in the TIR indicated this square footage of the bioretention area, but when we measured in the field, and I'll show you a photo of how that's measured, this was the actual area that was observed. The rest, some were larger, some were very similar, one was much larger. And then at the end of the list here, there was one that again was only about a half the size of what was indicated in the TIR. Also, for the ratio of bioretention area to basin area, the number of them were small, and granted, a number of those that were small were in fact retrofits with some latitude in the design, that these facilities did not meet the rule of thumb of 5% of the drainage area. But again, that's a rule of thumb, and each situation needs to be assessed individually. Here's another example of the weir measuring flow into the facility. Here's the hydrogeologic and geotechnical findings, really covered a wide range of conditions. The bioretention soil texture was generally coarser than the guidelines, and there's a wide range of infiltration rates. And the localized information about the facility hydrogeologic conditions often were not site-specific right where the facility was going to be placed. Here's an example of how we sampled the soil and the native soil underneath, collecting the soil for a sample, and then placing the well point in the hole with the stage recorder to monitor the groundwater fluctuations. Here's the result of the media composition, and you're probably familiar with this grain size distribution with the recommended grain size envelope in the dashed area, and each of the sites distribution of the BSM. And it's really indicating, this was the first set, indicating that in the fines, fines were less than what was recommended in the envelope. And those fines affect the spaces in between larger particle sizes to pass the water through. And so therefore this smaller size greatly affects the infiltration rate. Here's the same results from the second set. There were more so sites with fine sands and silts within the envelope, but still some not. And here's how we got the bioretention contact area in the flood test, the full flood test. And while the facility is flooding, Jenny and her hydrogeologists are able to calculate or measure actually the actual observed bioretention area in the facility. Here's another example. The previous one had a grate for the overflow, and the bioretention area would be up to the elevation of the grate. Here's another one. This one did not have a grate overflow, but actually the edge of the facility, the low point, represented the overflow that allowed any overflow to go out into this field. Here's a table of the comparison of the design model BSM and native infiltration rates compared to the field measured. And these are the values in unmodified. These are the actual expected infiltration rates ahead of the A saturation value that's in the model. And here's examples of what was expected for the infiltration rates between the BSM and the subgrade, also known as the native infiltration rate, compared to what we observed in the field. In a lot of cases, the infiltration rates of the BSM was greater, but in a couple of cases, they were actually less, like in this first facility and in this last facility, and maybe even in this, this facility here. And since these were fairly new facilities, this might indicate some effective compaction during construction or just being exposed to foot traffic. And Jenny can talk about that during questions as well. With the plants, this turned out to be very informative to do these plant assessments. Does somebody have a question? Anne really discovered that the cells were mostly planted with plants that grow in wetland or wet conditions, when in fact the units are incredibly well draining. They should be planted with more dry tolerant plants that can tolerate brief inundations of water, but not if the unit is located on still, which could set water up in the feet of the plant roots. But this was a common observation in the first set and in the second set, which has considerable ramifications on maintenance going forward for the owners. So in the vegetation finding, the shrubs did well, herbaceous species less so, and selecting fewer, more successful species will lead to greater survival. There is a recurring issue of plant die-off, and most interestingly, both for the plants and for hydrologic performance, there was evidence of uneven infiltration resulting in uneven moisture available to the plantings. And what we mean by uneven infiltration is that because the infiltration rate of most of these BSMs is fairly high, the infiltration largely happened near the inflows of the facilities, and in some cases, rarely, if ever, reached the other end of the facility, with the result of effects on survivability, but also potential bypassing of the infiltration, distributed infiltration, and bypassing straight to an underdrain. This was one of the more interesting observations we had in both the first 10 and the second 10. Doug is going to be talking about the hydrologic performance. You all know that it's meant to control flow and gain water quality benefits, but needs to be set up correctly. In the first 10, there were, without the bioretention module, there were a number of models used, and it's often not set up properly. And in the first 10, the performance of the modeling really was masked by just the size of the facilities, masking design errors or incorrect assumptions. The second set, 2012, was used, but in one case, the bioretention module for some reason was not. Again, models using the bioretention module did not have model parameters input properly, again, in a number of the cases. And the hydrologic performance of the facilities was more due to the small size of the facilities or low set overflow elevations. Interestingly, in the first set of 10, none of the facilities overflowed. In the second set of 10, 4 of the facilities overflowed, and each of those were underdrained, which would seem a little counterintuitive, but they were also small or they had low overflow elevations. For the most part, the model represented what we actually measured in the field quite well. Doug is recommending to ecology that maybe a vegetative litter layer and also increased evaporation rate could improve the performance of the model. And here's the take home, the simple design recommendations that I think each of you in this engineering audience will really recognize, that maintaining a bioretention top area of at least 5%. Again, that's very site specific, and take that with a grain of salt that kind of rule of thumb is, but we did see a number of the smaller facilities overflowing. Maintain a minimum 6-inch riser height. One of the facilities had a riser height of about 1 inch, and of course that doesn't gain you very much infiltration area. Make sure to meet the bioretention soil mix depth and particle size distribution. Again, importantly, specify a planting plan that reflects the relatively dry and well-drained conditions of bioretention facilities, and double check the accuracy and consistency of your bioretention soil media filtration and native infiltration rates and the associated correction factors. Those are going to have the greatest, obviously the greatest effect on your model outcomes. So we can answer a question or two right now before Doug does his slides on the model. Does anyone have a question they'd like to pose on these details?
I don't see any questions in the chat parts. If anyone has questions to Bill, feel free to unmute yourself and ask.
A quick question. So have agencies been changing their plant species that they allow? I mean, we can specify, but there's typically a list.
I don't know if we've had a question about that before, and there was an indication that the that is out there may be changing, and I don't know if Ann Klein is on the call. Ann, are you there? Okay, well maybe not, but you're exactly right. There probably will be, I would guess, as a result of our findings and otherwise, a little review of what those planting recommendations are. And I see a question, was the composition of the BSM 6040? Doug or Jenny, you want to reply to that?
Yeah, the BSM was mostly equivalent to a 60-40 mix. The organic content was pretty consistent. As Bill said, the fine sand content was a little bit out of spec.
Hi, Doug, Howie. We're going to pick on you in a little bit.
I probably shouldn't have joined in progress, I guess.
Have we looked at any without plants? I don't think so. None of our facilities had just grass. And, you know, one of the things I'm seeing and hearing about is the influence of the plant community in maintaining the tilth or the kind of aeration and organic content and infiltration capacity for the long term. Even though there's some questions that maybe fines coming in from the drainage area may plug the infiltration, there's actually a recent review paper out, just came out in the last 6 months, diving into that question of how plant communities maintain both hydrologic infiltration and even water quality benefits. But I think that for the long term, it's best to have some well-established plant community and not so much turf-like weedy species. Jenny, there's another question for you. Are you seeing the chat questions?
You know, I hear the bing, but I don't see the questions. It must be on a different screen. Would you mind reading it?
Yes, sure. From Chaim, that is question about the subgrade. I see that the alluvium subgrade had an infiltration rate not much lower than others. Did the construction remove and change the subgrade?
Oh, that's a great question, Chaim. So these are all built facilities, and most of them we don't have information on the quality during construction, how well they paid attention to temporary erosion sediment control or compaction. We did do hand augered soil borings through the bioretention soil down to either the subgrade or the underdrain rock, just to look at the connection. And we didn't see any obvious signs of construction silt or compaction on the subgrade itself. We did see for some of the narrower or smaller facilities, something that Bill mentioned, we did see edge compaction effects. And what I mean by that is the very narrow or small facilities, the bioretention soil was it was pretty obviously compacted along the rim, less compacted toward the center. One of our interpretations is that compaction may be just due to either maintenance or when plant or irrigation work was installed, there would have been a lot of foot traffic on the soil. But it was interesting to see that.
Okay, good, really good questions. Doug, do you want to work through your slides?
Yeah, I'll see if I can figure out how to do this here. Hold on just a second. And
I need to stop sharing mine, which I just did.
Switch over here to my screen and see if we got it up here. So what I'm going to do is I'm going to basically explain how we do the actual modeling of bioretention. This is going to be a very quick summary because I teach this in my AGC WWHM workshops and go through it in excruciating detail, but obviously we don't have time for that here. So I'm just going to give you basically a real quick run through. If you have questions and want to follow up in more detail later, you're certainly welcome to contact me even after this presentation. So bioretention, you know, we know it in many different forms and names depending upon where you are. They use different names, but basically they all work the same. And ecology has some very specific definitions. They have bioretention which means an engineered facility, as opposed to a rain garden, which is a non-engineered, you build it in your own backyard and, you can do whatever you want. But bioretention has very specific requirements. So, but the whole idea basically is that you're going to be able to collect water from the surrounding area, retain it on the site, and then infiltrate it in through your bioretention engineered soil mix. And then some of this water can evaporate back to the atmosphere. Some of it can infiltrate into the soil, and some of it's going to run off. So how it works is that we use this long-term infiltration and evapotranspiration to reduce the total stormwater runoff volume. So what happens between the storm events is actually even more important than what happens during them, because it's—
Hey, Doug, this is Jenny. You're not sharing the presentation.
Oh, we're not? Okay, well, let's see if I can figure out why not. Let me go back here and see what I need to do. So I shared my screen, but obviously it didn't come across. So
are you sharing your PowerPoint or just that desktop?
Well, I thought I was sharing my PowerPoint. So you're not seeing that?
Now we are.
You're seeing it now?
Yep,
Yeah.
now we see it.
Okay.
But it's not on slideshow mode.
No, I'm just going to go over to that now. So let me switch back over here. So are we good now?
Yes.
Perfect. Yep.
Okay, well, I'm glad somebody finally mentioned it. Otherwise, I would have continued on my way. So these are the different names for bioretention, just to summarize. Ecology, like I said, has a specific definition of what bioretention is, as opposed to a rain garden. And the water obviously has a variety of options when it gets into a bioretention facility. So it can either infiltrate into the soil, go back to the atmosphere, or run off. And this is where these dry periods allow water to both infiltrate into the native soil if possible, or go back to the atmosphere through evapotranspiration. So we can do a number of things with bioretention. Ecology has a number of requirements when it comes to stormwater. Minimum requirement number 5 is related to LID facilities and flow control. 6 is water quality, and 7 is stream protection. So you can use bioretention to meet either 1 or 2 or all 3 of these requirements if that is your goal. Now, the way it works in the model in WWHM is it uses HSPF, which is continuous simulation hydrology. So all the Western Washington hydrology model is a package that allows the user to easily use HSPF. And so this means that we can model the entire hydrologic cycle over multiple years at a 15-minute time step. And this is what we're doing here with our bioretention facilities. So when we did the actual monitoring, we monitored them at a 5-minute time step. We only had about 9 months worth of data, but we were still able to basically model them at that time step. So we have that flexibility. And that means that we can basically watch where the water goes through the whole hydrologic cycle. So this is what the actual input looks like for the bioretention element in WWHM. And so we have a lot of options here, a lot of things that it can do. And I'm not going to go into all the details of all this just because of the time limitations that we have here. But this is basically how it works. You have rain on the facility, you have flow coming in, you have surface ponding, you can have surface runoff, and then the water can go through the different layers. So we have up to 3 different layers. This can represent the bioretention soil mix, a gravel layer underneath that, and whatever else you may want to have. You don't have to have 3 layers. You can certainly have less. You have the option of having an under drain and you also have the option of having infiltration into the native soil underneath. Now the water's got to go somewhere. So if it can't infiltrate into the native soil, you have to have an underdrain to get rid of it. If you do have infiltration into the native soil, you can still have an underdrain if you want. So there's a couple things to be aware of. The bioretention area in the model automatically gets rain and evaporation on that surface area. So you don't want to include that area in your drainage that is contributing to it. Ecology has a very specific soil mix layer that is required, and that is set up in the software so that you can do that. And as I mentioned, the underdrain is an option, and if you do have an underdrain, you have the ability to put an orifice control on it to basically control how much of that water, how quickly it comes out from the underdrain. So ecology also includes a safety factor for the bioretention soil mix, and this is called this KSAT safety factor. And basically it's going to be either 2 or 4, and this is a factor that basically decreases the calculated infiltration rate through the bioretention soil mix itself. And so depending upon the size of the drainage area to the facility, if it's larger than these values that are shown here, then you need a safety factor of 4. If it's smaller, then you just need a factor of 2. This is to basically try to account for the fact that over the entire life of the facility, let's say you've got a 50-year life for this facility, that in time you have the potential of clogging on the surface, which is going to reduce the infiltration rate. So this is a policy decision that the Department of Ecology made in terms of how to deal with that situation. Now, when it comes to the bioretention performance, there's a number of critical factors. So I'm just going to quickly go through these. Surface ponding's one. Obviously, if you can have the water coming in, sit on the surface without it automatically draining off, you have the ability to store some water, give the water more time to basically go down through the soil and then go out either through an underdrain or to the native soil. So this is where, as Bill was saying, having a 6-inch height of your riser, which means that you can get 6 inches of surface ponding before you actually get surface runoff, is a benefit and something that you should keep in mind. If you only have 1 inch, then you're not going to get nearly as much ponding. So surface ponding gives you some temporary surface storage, and obviously you want some storage, but you don't want too much ponding there because you don't want to drown out your vegetation. So that's a key consideration. Another one obviously is what type of soil mix you have. Now, like I said, ecology has some specific rules for that top layer, and that's at 18 inches of the bioretention soil mix that Bill mentioned. Below that, you can have a second or a third layer. Oftentimes there's a gravel layer underneath that, which is primarily used for storage. But the user has the ability to specify exactly what these layers are, and we give you a lot of flexibility there. The goal is basically to use that engineered soil mix to provide the water quality treatment. So you don't want to have a mix that basically prevents the water from draining too quickly, because then you're going to get more surface ponding and then surface runoff. But if it just drains right through it like it would through gravel, then you don't get the water quality treatment that you're looking for. And then once the water gets down into that soil, like I said, it has to go somewhere. So you have the option of having an underdrain, and if you have an underdrain, then the water has the ability to exit the soil through that direction. And so that's a key component. And so there's a couple things that you need to make sure that you take into account in terms of how you place the underdrain, and then basically how quickly that water can be discharged from it. And we give you the option of setting that under drain height to whatever height you want above the bottom of that bottom soil layer, and also whether or not you want to have an orifice that controls the discharge from that under drain. And then finally, the infiltration into the native soil. If you have the ability to infiltrate into the native soil and it's not going to cause problems, then that is certainly a good option, and that obviously depends upon what type of soil you have down there, but it's certainly something worth considering, and that will make a big difference in how well your facility functions. So the bottom line is that, like I said, that water has to go somewhere, and if you can infiltrate the native soil, so much the better. In terms of actually how we do the modeling, we do it from a top-down approach. So this is all internal in the calculations. You don't have to deal with any of this detail, but just to give you an idea, when the water first is applied onto the soil, we actually do the calculations based upon the properties of the different layers. And so depending upon what those properties are, the water can move either quickly or slowly through that soil, first of all going into the top layer, then the second layer, and then on down, and eventually getting down to where it can go out through an under drain or to the native soil. So they govern how quickly that water can then move. And so this is done, this is all done, calculated internally in WWHM based on the Green-Amp equation, and then also using Darcy's and the Van Granouten equations. So each soil layer has its own separate set of calculations based upon its individual set of soil properties. Now, what happens in the real world is that when you don't have any water in that soil, you have that vapor condition where basically you have a lot of void space. That's the first place that water will fill up. And then as it does fill up, eventually then when it gets to the saturated point, that's where you actually get water draining from one soil layer to the next. So what we're doing basically is calculating how quickly that occurs. And so that's based upon the type of soil mix that you have and that depth. So we have this standard here, this SMMWW. So it's the soil mix for the stormwater manual for Western Washington, which is 12-inch per hour standard. And that is what you should be using for that top layer. But we have a variety of different soil mixes that are available that you can pick for the other layers also. These are the parameters that go with each of the soil mixes. Now, you don't have to know all this information, but this is what's in the model. And here's a table that we have that we use to basically determine what the parameter values are. So all this information is available. If you want to use it, it's there for you. You can create your own soil mix also, but you just need to have the parameter values that are for these different parameters. So it's a little bit of work, but the bottom line is that when it's all said and done, and this is all calculated for you, it comes up with what we call a stage storage discharge table, or an HSPF, what would be called an F table. And we have one for that surface ponding and then one for the subsurface layer. And so this is how internally in WWHM the water is modeled in terms of how it moves through the different soil layers and then can discharge both via surface discharge and also through the infiltration process. So all these are calculated for you, but you have the ability to basically change this based upon your input. So yes.
This is Bill. Just a quick question to clarify. You're saying that there's some options to choose from, but really in Western Washington, to be in compliance with the Stormwater Management Manual, the main first steps is selecting the SWIM 12 soil, and a K saturation value of either 2 or 4, and there's really not much flexibility around that?
That is correct. I mean, that's based upon ecology standards, but you can have additional layers below that of different soil mixes, anything, sand, gravel, whatever you think is appropriate. So you have that option.
That initial BSM, though, is kind of the treatment layer that they're really wanting to apply to that first infiltration and water quality treatment. And that K saturation value is to take into account the I'll say, theory or expectation that there is clogging over time, but you called it a fact that, but I'll weigh in that there's maybe some debate about what degree that clogging may be. We had the city of Seattle green stormwater infrastructure lead saying that they're finding that with aging, the infiltration rate sustains itself or actually increases.
Yeah, that's a policy decision on ecology's part. And that's, like I said, that's a KSAT safety factor. So it's basically used to reduce the assumed infiltration rate, but it was based upon, ecology's decision to be conservative in terms of what you can expect long term. So
right, thanks for that.
If people have, comments on that, they should direct that to the Department of Ecology. Basically, this is the end result here in terms of actually how the actual routing is done through the bioretention facility. And this allows for both discharge through surface ponding and also through infiltration into the native soil and out through an underdrain if one's available. So we give you all that flexibility, and it's just a matter of inputting the appropriate and hopefully correct input to generate then the correct output that you get from the model. So basically we did this, and this was all based upon like those 10 sites that Bill mentioned earlier, and we then compared our results with what we measured out there in the real world, and there were obviously some differences, but in general we pretty much were able to reproduce what we saw out there, and we have all the details in our report. So if you want to see graph after graph after graph of this sort of information, it's all available in the report that we are just finalizing, and it will be out at the end of the month or early next year. So basically, as Bill said, these are the key considerations here in terms of when you're setting up your bioretention area in your model. 5% is a good rule of thumb, 6-inch riser height, and 18 inches of the ecology bioretention soil mix. Do those things and you really can't go too wrong, but those are certainly the key things to consider as you do your modeling. So that is basically the summary of a quick overview of the modeling work. And if you have questions, here's my contact information. Joe Brasher, who he and I are co-founders at Clear Creek Solutions. He's the real brains behind the Western Washington hydrology model. So if I can't answer your question, I'll pass it on to him. Our contact at the Department of Ecology is Firuza and Labib, and also people like Doug Howie and others there also are very knowledgeable on this subject. So I will finish up there, and we'll open it up if we have any time for questions. I'll be happy to answer them if I can.
Thank you, Dart. For those who have questions, again, feel free to post them on the chat. Dart and Bill, are you both able to see the chat?
I'm not seeing it right now, but I assume that somebody can see it.
Bill, you're unmuted. Bill, you're muted.
On your toolbar, Doug, there's a little.
Oh, okay. I can see the meeting chat now. Yeah.
So this next question from Lisa, this might be for you, Jenny. Do you know about whether anyone made their own mixes or purchased it?
That's a good question. For 4 of the facilities, we do have some records from construction, and that was a mix that was purchased. I don't know about the other 6. We didn't have construction records for all of the sites.
And again, for the BSM, the selected media is not a whole lot of range of options. It's supposed to meet the BSM swim 12 criteria, right?
Well, in a perfect world, yes.
Doug, I have a question for you on using WWHM. Do you, for the projects where you need to have HSPF parameters calibrated, do you do that in HSPF before you run WWHM, or is there a calibration process within WWHM?
The way we've set up the Western Washington hydrology model is we have already in the model calibrated parameter values for Western Washington. So these are based upon, a variety of studies that have been done pretty much all the way from Whatcom County down to Thurston County, and have, as a result, developed a set of parameter values that are good in representing the hydrology that we see pretty much throughout Western Washington. And Clark County has some different soils, and we've done some different calibrations down there and come up with different parameter values. And if you're doing work down in Clark County, then you should be using that version of our software, and that has those parameter values built into it. So the user doesn't have to do calibration. I mean, you could certainly use the software to do a calibration. And obviously, if you're trying to do a project over in Eastern Washington, you have different soils over there, different climatic conditions, and I wouldn't recommend just taking our parameter values and using them over there. But anywhere in Western Washington, you don't need to do a calibration.
You see the next question from Keith?
So yeah, ecology is, so do you recommend we account for the 3-inch of coarse compost material at the top of the bioretention soil mix? And basically you can do that as your layer number 1 now. Ecology has basically come up with that information or that decision. They've not asked us to incorporate it into the software. So it's kind of up to the user as to how they want to proceed to do that. That's something which, the next time we revise the software, hopefully we'll be able to incorporate something like that specifically in there, so it's more convenient for the user.
So do you think that layer would have a large effect on the overall outcome?
Well, we saw that in some of the sites, I think 3 of the sites, that there was something on the surface that was causing more ponding than we would expect. And so I attributed it to some sort of leaf vegetative layer that was basically reducing the amount of water that could go into the bioretention soil mix. So I assume that something like a compost material would act somewhat the same. But, we don't have a whole lot of information at this point.
Okay.
What's the basis or background? Oh. Somebody just put a question in here about the Well, I can't see the question now, but there was a question about the, let's see if I can scroll back up here. The basis or background for the 5% surface area requirement. It's not a requirement. It's just that it seems like it's a fairly good rule of thumb to get you started. You can certainly vary from that as long as you still meet whatever minimum requirement you're trying to achieve. But at least it gives you an idea of where to start. It's, as you design bioretention facilities, you'll find that it's an iterative process. So you'll put in what you think is appropriate for your particular site, try it and see if it works. You may decide that you need to have your site larger or smaller, but you need somewhere to start. So 5%, it just kind of gives you the idea of where to start your process, and then you can go from there. You know, it's not something that any agency is going to hold you by, but it gives you an idea kind of what to expect. There's a question here.
Doug Howie, can I comment on that for a second?
Yeah, go ahead, Doug.
The 5% really only applies in the list option for minimum required number 5. So if you're using the list option and bioretention is feasible, then you have to make the bioretention at least 5% of the area draining to it. That's so we don't have somebody just come out there and put a 5 square foot bioretention facility. We wanted to give a minimum size to that. Now that 5% is close to what would be needed if you were meeting the LID standard, performance standard. You need somewhere around 8% to meet the LID performance standard. So using a list option, you're not quite meeting the performance standard, but we're getting a minimum size. Now to meet minimum requirements 6 and 7, you're going to be making those appropriate for the site, and starting with 5% is a good place, as Doug explained. But the requirement for the 5% is only in the list option.
Yeah, and to clarify, if you go with a list option, you don't have to do any modeling.
Right.
So that's the alternative approach. Okay, there's a question here about ponding. Our adopted manual requires a range of 6 to 12 inches. Is that a good maximum? Only a minimum of 6 inches is required. Well, you know, this is where, you know, you can have a policy decision, which is apparently what their adopted manual is, that, you know, gives you a range, and that's fine. We're just basically saying at least have 6 inches. If you want to have more than 6 inches for ponding, that's fine as long as you don't flood out all your vegetation. So you don't want like 3 feet of ponding depth or something like that. But once again, 6 inches kind of gives you an idea of where you should start, and then you can certainly adjust it from there. If you can get 12 inches, so much the better.
The Doug Howie jumping in again. You got a 72-hour drain. It has to drain down within a certain amount of time. So your depth kind of has to tie into the infiltration rate into your into the ground, so that you can drain. If you have too low an infiltration rate into the ground, 0.3 of an inch, you can only have 6 inches because it takes too long to drain that 6 inches down so it's dry after that maximum period of time. So you have to look at that for your depth as well as the plants.
So there could be a maximum overflow depth based on that time limit.
Correct. You may be limited to 8 inches because of the time limit.
Good comment.
There's another question here about the orifice diameter parameter for the underdrain. So what's that intended for? And basically the idea is that you have the ability to constrict the outflow from the underdrain. Now, if you set the orifice diameter to equal the same size as the underdrain diameter, then basically you don't have any restriction on how much water comes out, and then it's purely a function of the underdrain itself. But if you want to limit that flow coming out from the underdrain because you're getting too much to meet, in particular, minimum requirement number 5, then you have the ability in the model to basically specify a smaller diameter for the discharge calculations for the underdrain, and then that will decrease the amount of water that comes out and helps you then try to meet minimum requirement number 5 and potentially minimum requirement number 7. So that's basically what it's there for. If you don't need to use it, set your orifice diameter to the same size as your underdrain diameter.
And similar to that, Doug, we've talked about how the model allows for the underdrain to be elevated off the bottom. And so in a secondary effect, there could be some pooling in that case before it starts to flow out.
Right, you can set your underdrain to any height you want. So if you want to set it a foot above the bottom of your facility, that's fine. And then obviously it's not going to start draining out right away. The caveat there is that if you don't have infiltration to the native soil and you have the underdrain raised, all you're going to do is fill up that water, that storage below the underdrain in the initial part of the simulation. And if the water can't go anywhere, if there's no infiltration into the native soil, then basically it just becomes dead storage. So it doesn't gain you a whole lot from that perspective. If you've got infiltration into the native soil, then you're going to be able to continually drain water out that way. And then that will be the primary way that water will exit out of your bioretention soil, and the underdrain will be sort of the secondary outlet, obviously depending upon the infiltration rate to the native soil.
I think we have one last question. I don't know if you want to take 10 or 15 seconds to answer really quickly.
Yeah, did I not see that? Oh, here we go.
Okay.
How should uneven infiltration, particularly at the inlet, be mitigated? Yeah, that's something which obviously we don't have the ability to specifically model. That is more of a function, I think, basically of how you put your inlets relative to where your outlet is, your surface discharge outlet. So that is something which is going to be site specific. And as Bill mentioned, with the vegetation, you want to put the vegetation in places where it will, be the right vegetation for the right location. So if it's more water tolerant, put it near the places where the water's coming into the facility as opposed to some portion where it's not going to get very much water.
Okay. Well, appreciate that, Dodd. So we're on the hour, so appreciate everyone's questions and discussions. Dodd and Bill, you shared your contacts in the presentation. So we did record this session. We'll post it on YouTube. And I would like to say thank you to both Dodd and Bill for an excellent presentation and a great conclusion of 2020. And thanks everyone. We will have great speakers in 2021. We still have 1 or 2 open spots. So if anyone on this call would like to present anything to this group, please contact Michelle or myself. And our next our next brown bag will be on January 7th. So we'll kick off next year with another excellent talk. So looking forward to that. Thank you, Bill and Dodd, again, and for your team who's been also contributing to this presentation. And with that, I'll like to thank you everyone and have a great holiday, and we'll see you next year.
Thank you.
Thanks, Simon. Thanks all.
Thank you, guys.